Today we're going to take a look at the mean value theorem and Rolle's theorem. The mean value theorem is a theorem that we can use to show that if we know the average rate of change of a function between 2 points, if I know the average rate of change, then somewhere on that graph we know the instantaneous rate of change has to be the exact same. So we know that the instantaneous rate of change has to be the same. So that's what the MVT says. It just says somewhere our average rate of change has to equal our instantaneous rate of change. There are some caveats, there are some rules to this. One, we say the function has to be continuous on a closed interval. And two, differentiable, which means the derivative must exist on an open interval. The reason we say open, because we don't like to use endpoints. We talked a little bit about that yesterday when we talked about the extreme value theorem. Slopes don't exist at endpoints, so we have to keep that as an open interval. Now, if the function is continuous and differentiable, then there are three things that we can say. One, One, that the instantaneous rate of change has to equal the average rate of change. What does that mean for us? Well, that's the slope of our tangent line. This is my tangent line right here. If I find the slope of that line, that's our tangent line. Well, this one requires 2 points. That is a secant line. What we're saying is that these two are going to be parallel to each other. That if some point, the slope containing these 2 points will equal the slope at exactly 1 point on our graph. Now, where is this applicable in life? Well, it's like your car. If my average speed is 50 miles per hour in a car ride, well, at some point, my instantaneous speed must also be 50 miles per hour. So, and that's what it says for us. So we like to say the instantaneous rate of change equals the average rate of change. Over here, we have a formula for it. In other words, we're saying that the derivative equals the slope. This is just our slope formula from earlier, change in y over change in x. So let's look at an example here. Let's kind of see how we really apply this. Let's say we are given a function, f of x equals x squared plus 1, and we're on some domain 0 to 2. Let's sketch the graph below and show what the MVT is trying to tell us. So I am going to sketch this graph, the parabola, on the domain 0 to 2. If I plug in 0, I'm going to get 1. That's pretty easy to do. If we plug in 2, we're going to get 5. This is a parabola, so it's kind of a smooth function, just like butter. I can connect these 2 points, like so. And that's going to give me a slope of a tangent line. And I can find the slope of that tangent line. That's just a change in my y values, 5 minus 1, over the change in my x values, 2 minus 0. And that's going to give me 4 over 2, or 2. So this is what we call the average rate of change on the domain 0 to 2. What we want to find is another line somewhere in the middle, somewhere in between 0 and 2, where the slope is exactly the same. So in other words, if I were to graph a tangent line that has the exact same slope as what we just found, and it looks to be about right here. So I know that somewhere around right here, there is a C value that we're going to call it, where the slopes are exactly the same. Well, how can we find C? And that's the question today. How can we find that C value? Well, it's not really hard to get if we understand what we're looking for. Remember, we want to find out where the slope is equal to 2. Well, we know what find slope, so we want to find out where the derivative of our function equals 2. The derivative here is going to be 2x. Set that equal to 2, and we know that the x value has to be 1. So therefore, we're saying at x equals 1, the instantaneous rate of change will equal our average rate of change. And that is what we call the mean value theorem. So how do we actually apply this? And we wish it was that easy, but it's not always that way. So let's see here. For the example above, let's show that the mean value theorem applies, and then find C that guarantees the theorem. So the second part's going to be all the same, but we just have to show that we can use the mean value theorem. And to do that, we have to say, 1, is the function continuous? And yes, this function is going to be continuous on this domain. So we're going to say f of x is continuous on the domain 0 to 2 and differentiable because it's a smooth function on the open interval. Don't say a to b, that's terrible. On the open interval 0 to 2. Now you have to mention closed and open. You got to mention those. Therefore, we can say that the MVT applies. And on the interval 0 to 2, we're saying that the instantaneous rate of change will equal the average rate of change. That's somewhere on that interval, that's going to be true for us. So now we just have to find where that's going to occur. So to find out where that's going to occur, that's exactly what we did here. So to find out where that occurs, where does the instantaneous rate of change equal the average rate of change? I'm going to make this a little bit longer than this time. We will say that the instantaneous, that's our derivative, equals our average. Well, the average rate of change, that's just our slope formula, f of b minus f of a over b minus a. So I'm going to take my derivative, which is easy, 2x, and plug in my values. I'm just going to do this. Plug in this case, we want f of 2 minus f of 0 all over 2 minus 0. And if we plugged in 2, well, we already knew that was 5. Plugged in 0, we knew that was 1, and that just becomes 2. And, of course, we got 2 when we did all this. And we get x equals 1. Now, they say find c, but, you know, c is just some random x value. So I guess we should say c. So, therefore, c is 1 if you want. They're not going to be too picky about that. So let's try another one. Ready? Okay. For the following, show that the mean value theorem applies. And then, of course, find our c again. We want to find that x value. Now, for this one, I'm going to use product rule. I'm actually going to expand it. X cubed minus x squared minus 2x. So the first thing I want to make sure is that the mean value theorem can be applied. And I ask myself, is this a continuous function on our domain? Yes. Is it differentiable on our domain? Yes. So I'm going to say f of x is, whoops, not equals, is continuous, don't abbreviate, on the domain -1 to 1, and differentiable on the open interval -1 to 1. Again, open, and therefore we're going to say MVT applies. And somewhere on that interval, and somewhere on our interval, -1 to 1, notice I'm going to use a soft bracket here, we're going to say that the instantaneous rate of change equals our average rate of change. There's our answer. That's it. We're just going to leave it like that. But now we got to find, of course, where. So to find our c here, we're going to say, take our derivative, set that equal to the slope, f of 1 minus f of -1 all over 1, and that's just going to become plus 2. But plus 1. 1 plus 1. Come on. There we go. Our derivative, I got that already. That's just 3. That's a weird looking 3. 3x squared minus 2x minus 2 equal to, plug all this in, plug in a 1 here. If you plug 1 in, you're just going to get 1 minus 1, which is 0, minus 2. -2 minus, plug in -1, we get -1 plus 1 plus 2. So we get +2 all over 2, and that, of course, becomes -4. So I got to do a little bit of math here. Terrible, terrible stuff. So that's going to give me 3x squared minus 2x. Bring this over, plus 2 equals 0. And we're going to have to factor. Did you notice I made a big mistake here? So let me see if I can fix it. It was when I plugged in the negative 1. I changed the sign here. If you take a negative 1 and plug it in, this should become, whoops, let me erase all this here, get rid of all my evidence here. If you plug in a negative 1 here, we get negative 1 minus 1, which is negative 2, plus 2. So that should become a 0, and this becomes negative 1 right there. And if I bring that negative 1 over, this just becomes minus 1 right here. And that is a lot easier to factor. So let's go ahead and factor that. We're going to get 3x, an x, 1, 1, negative, positive, and you're going to get x equals negative 1/3 and x equals 1. And when we solve it, take a look at your domain, make sure that they both work. We got negative 1 to 1. So this one works, but unfortunately that's an endpoint. Therefore, it's out of our domain. So the only one that's going to work is this. So what that says is this guarantees at this point the slopes are going to be the same. So what that means, like the slope of my average value and the instantaneous slope is going to equal negative 1 at that exact point. So let's go ahead and take a look at number 2 real quick. Same thing, this function is continuous and differentiable, so we can go and say that f of x is continuous on the closed domain, negative 2 to 3, and differentiable on the open interval, negative 2 to 3. Therefore, you have to say this following, MVT applies. And on our domain, negative 2 to 3, we're going to say that the instantaneous rate of change has to equal the average rate of change. We just have to find out where that occurs. So I'm going to do that. Ready? Find out where. We are just going to take our derivative and set that equal to the slope. The average rate of change. Slope, average rate, derivative, average rate of change. F of 3 minus f of negative 2 over, and this just becomes 3 plus 2. Take our derivative, 2x minus 1. That's going to equal, do some math here, plug in 3. We get 9 minus 3, which is 6, plus 6 is 12. Minus, plug in a negative 2, we get 4 plus 2, which is 6, plus 6, which is 12. Oh, this is nice, over 5. And that's just 0. And if I solve that, we just get x equals 1/2. Now, they do say find c, but if you say x equals 1/2, we're okay with that. Or therefore, c equals 1/2. Either one's fine. Pretty easy to do. All right, so let's take a look at number 3. Now, here's a problem for this one. Notice, I'm dividing here. So I want to run the risk of a domain restriction. And I do have one here. X can't be 0. Which is really kind of nice for us, honestly, since we can't be 0. Look at the domain. We're done. The domain goes from negative 2 to 3. 0 is in the middle there. So we can say f of x is not continuous. And I'm going to say at x equals 0. You can even say not differentiable because it's not going to be that either. Therefore, we're going to say that the MVT fails. So if you check your domain restrictions, sometimes you get like, oh, look, that's pretty easy. All right, so let's take a look at number 4 right here. Oh no, I put my domain on this one. So let's make up our domain. On the domain, let's go negative 1 to 1, 2, 3, 4. 5. Let's go from negative 1 to 5. There we go. Sorry about that. Now this function from negative 1 to 5, it does have a domain sorry, that should be negative 1. It should be positive 1. We'll make that a positive 1 there. There. And a 5. Everything keeps erasing. There we go. We'll go from 1 to 5. Now this does have a domain restriction. I'm going to check it again. X can't be 0. But I don't have to worry about it because I'm starting at 1 and not anything before that. That's why I fixed it to a positive one. So this function will be continuous, so we're going to say f of x is continuous on the domain 1 to 5 and differentiable on the open interval 1 to 5. Therefore, we're going to say that the MVT applies. And on our domain 1 to 5, we're going to say that somewhere the instantaneous rate of change has to equal our average rate of change. We just have to find out where that occurs. So to find out where, we're just going to take our derivative, f prime of x, set that equal to the function, f of 5 minus f of 1 over 5 minus 1. Our derivative, that's not that bad to do. We're going to get 0, derivative 3 is 0. Now we know the shortcut, the derivative of 5 over x. Remember, if I want this is negative 5x to the negative 1 or 5x to the negative 2. So we're going to get 5 over x squared equals, plug in the 5. This becomes 3 minus 1, which is 2, minus, plug in the 1. Plug in the 1. This becomes 3 minus 5, which is a negative 2, and that's going to be over 4. So therefore, we would get 5 over x squared equal to, what's that going to become? 1, or x squared equals 1/5. And taking the derivative, taking the square root, x becomes plus or minus the square root of 1/5, but I don't want the minus, because that's out of my domain, so we only pick the positive. Don't pick the minus, we only want the positive right there. Alright, I hope you guys enjoyed mean value theorem. Come to the next video, we'll talk about Rolle's theorem. See you then.